Okay, so we've talked about the state of stress for 2D problems. For 2D problems, there's just three unknowns, N, V, and M. Those are the three internal loads. If we cut a two-dimensional beam, we draw N, V, and M. We can solve for N, V, and M. We can look at the stresses caused by N, the stress caused by V, the stress caused by M. And the stress caused by N and the stress caused by M are the same type of stress. They are normal stresses. And we can combine those similar stresses because they're the same direction, same type of stress. So for 2D, the state of stress, the normal stress is the N over A plus the My over I. And the shear stress is the VQ over IT. Okay. But what about in 3D? Let's think about this in 3D because it gets a lot more complicated. But it's really interesting, fascinating. I don't know if you will agree. But in 3D, instead of just N, V, and M, we have three forces and three moments. All right, we have three internal forces and three internal moments. We did this second week of class. We cut it in 3D. We can solve for the three forces and the three moments. Let's define some axes. So let's call this X, Y, and Z. So we can have one force Fy that is perpendicular to our cut. This is the N, right? That is the N force. We'll call it Fy. And then we've got another force Fz and another force Fx. And those two forces are both shear forces. Those are both shear forces. So now in 3D, we don't only have one V. We really have two V's. We have the shear force. So this is like a normal. This is a V. This is a V. We have one shear force that we're used to. That's kind of the shear that we're used to. But then we have this other shear force that's kind of coming out of the page. It would have been coming out of the page for our 2D problem. So, all right, so we've got those three forces. And do you see, I took, I think, a picture in the book and kind of edited it, cropped it, cut it, made it my own. But do you see what type of stresses each of those forces cause? The force that is perpendicular to your cut, so it's not always in the Y. It depends on how you define your axes, but the force that is perpendicular to your cut is the N. It has a normal force of F over A. It has a normal force of F over A. The other two forces are shear forces, and those have stresses of V Q over IT. This would be V Q over IT. All right, but this would be, I'll say it's in the Z direction. This would be in the X. We should even say it's in the negative X direction. It's in whatever direction that shear force is in. That's the direction of the shear stress. Did you get that? Whatever direction the internal shear force is in, that's the direction that the shear stress is in. But we cannot combine those two. We can't. One's in one direction, one's in another direction. If we really, really, really wanted to combine them, we would need to do A squared plus B squared and say, okay, these are at C squared at this direction at some weird angle. I would keep those separate. I would not combine those because they're in two different directions. One's in the Z direction, one is in the X direction. Let's look at the neutral axis, though, because this Q is Y bar prime A prime. And to get A prime, you need to know, and to get Y bar prime, you need to know where the neutral axis is. The neutral axis for, maybe we'll write this down, the neutral axis for shear forces is perpendicular to the shear force. So do you see that this would be the neutral axis for that one, but we need to turn it on its side. That would be the neutral axis for that one. Okay? So, this thickness it depends on what point we're looking at, because we could be looking at that point or that point or that point. But anyway, you just kind of have to rotate your head 90 degrees, whether you're looking at this is kind of what we're used to looking at, versus over here when we start looking at a shear that is in the perpendicular to what we're used to looking at. The neutral axis would be straight up and down. The eye would be the eye about the neutral axis. We're used to doing the neutral axis, horizontally. This is neutral axis vertically. Now, circular beams, though, most of the times those eyes for a circle is the same, whether it's IX or IY. Anyway, this thickness needs to be thickness along the direction of the neutral axis. Okay, so the three forces create those three types of stresses. The force that is perpendicular to my cut is the normal force. It creates a normal stress, force over area. It's uniform, so it really doesn't matter whether I'm looking at that point or that point or that point or that point or that point. Its stress is force over area. But when I start looking at these shear stresses caused by these shear forces, it really does matter. If I'm looking at that point, then that, even if this could be a very large force, Fz, that right there would be 0 up there at that point, because we know that shear stress, VQ over IT, it's a maximum at the neutral axis, and it gets further, less and less and less, until it gets to the very top, very bottom, it's 0. Whereas if I'm looking at that same point, then this force would cause a large VQ over IT. All right, let's think about this green point right here. What about this point? If I'm looking at the shear force right there, it's on the neutral axis. It has a large magnitude right there of VQ over IT. But that same point, when I think about, okay, well, what's the shear force what's the shear stress caused by the X shear force? It'd be 0, right? It'd be 0 because it's furthest away from the neutral axis. Okay, so sometimes you kind of have to, tilt your head 90 degrees to think about what is the stress at certain points. Okay, now moments. Moments, a lot harder, I think. First of all, we have this moment in the y direction. A moment in the y direction is as if my right hand, my fingers are curling about the y-axis. So take your right hand and curl your forefingers about the y-axis. And so that type of moment, my thumb is pointing in y, right? For moments, the direction that my thumb is pointing is the direction of the moment. For those types of moments, the moment that is curling about the y-axis, it's not always y, but it's the axis that's going straight down the middle, down the barrel of your beam. That is the torsional moment. And that moment, we've talked about, creates the TR over J stress. TR over J. Remember that? Remember the shear stress caused by a torsional moment is TR over J. That's what this moment, so instead of saying TR over J, it's M R over J. So this creates shear stress of M R over J. And it is, do you see how the magnitude is drawn on here? If I'm asking for what's the TR over J at the very center, it's 0 because it's R at the very center, it would be 0. But if I'm asking for it at that point, I need to calculate TR over J. If I'm asking for it at that point, TR over J. That point would be here, this point would be here. Do you see that this moment gives you the direction of the shear stress? So if it's this type of moment, if it's, my right hand rule, if fingers are pointed counterclockwise, then at this green point, my stress would be straight down. At this blue point, though, my stress would be straight to the left. So that would be the shear stress caused by the torsional moment. The other two moments are bending moments. These are moments that, imagine I've got a pool noodle. These are moments that would bend the pool noodle into a smiley face, or in this case, the three-dimensionalness that we haven't had for our two-dimensional problems would be this one right here, which would it would bow outward, right? It would bow outward into or out of the page, into or out of the paper. Okay, so this right here, this moment right here would be my MX, the moment that is rotating using the right hand rule. My fingers start rotating. My thumb is pointed in the X direction. So this would be an MX. This would be an Z. This would be an MZ right here. And these types of moments are bending moments. These would create MY over I, MY over I. So this is MZ, this is MX. Now that Y, is it really Y? That Y is the distance from the neutral axis. Here is the neutral axis for my bending moment right there. Or here is the neutral axis right there. So here's another thing to know. The neutral axis for bending moments is in the direction of the bending moment. Do you see that? The Z bending moment has the Z axis is the neutral axis. The X bending moment, the X axis is the neutral axis. All right, and so if we're points, so let's think about this. All right, so let's kind of go back to, okay, what if I've got a blue point? What if I'm looking at the very top? Well, for this MX, yes, I would have some compression at the very top, MY over I, because here's the M. What's the Y? The Y would be the distance from the neutral axis to that point, and then the I is just the shape. It's the I about the neutral axis. Versus, okay, what if I was looking at the same point, but I want to say, okay, what is my MZ moment? What type of stress does my MZ moment create about that blue dot at the very top? The answer would be 0. Even though my bending moment could be 1,000 kilonewton meters, but at point B, the Y value would be 0. It's on the neutral axis. It doesn't have any tension or compression on the neutral axis for that Z moment. And then, but that same point, yes, it would have some shear stress, TR over J, to the left. All right, how about the green dot? How about the green dot though? The green dot right here, well, my MX would not create any stress, but my MZ would create stress because now the Y value is this way. The Y value would be that magnitude right here, and then down here, the shear stress would be down. Okay, 3 forces and 3 stresses, three forces, 1, 2, 3, 3 moments, 1, 2, 3, all create their own type of stress. You know, that force creates that stress, that force creates that stress, that force creates that stress. This moment creates that stress, this moment creates that stress, this moment creates that stress. Okay, we can combine, I'm going to come back to this. We can combine similar stresses in similar directions. Okay? We can combine normal stresses in the same direction. So, here we go. These 3 stresses are all normal stresses. The normal stress caused by N, the normal stress caused by bending moments. They are normal stresses. They are all perpendicular to the cut. We can combine them. We'll be very careful. Some might be in tension, some might be in compression, but we can combine them and say, okay, the total normal stress is this. You know, I had positive 55 MPa over here. I had negative 14 MPa. This one, it created 0 because I'm just looking at this point. It's on the neutral axis, so there's no bending stress on the neutral axis. But anyway, I can combine all the normal stresses into one normal stress. All right? And then, for shear stresses, I've got to be very careful, but I can combine shear stresses if they're in the same direction. All right? For instance, this blue dot, I can combine this shear stress with that shear stress. Now, one is left, one is to the right, so be careful. One's positive, one's negative. But I can combine those into one shear stress in the x direction. Now, I would not combine it with this one. First of all, this one right here is 0, so obviously I wouldn't combine it. But this one would be up-down, and I wouldn't combine a left-right shear stress with an up-down shear stress. Did you get that? Don't combine a left-right shear stress with an up-down shear stress. If you really, really wanted to, you could combine them at an angle. It'd be, like an x and a y, a squared plus b squared equals c squared. And you'd have to specify what angle they're in. I would not want you to combine them at all. Okay, but if they are in the same direction, you can combine them. How about this green dot? This green dot, I would combine this down shear stress with this down shear stress right here. This one I would not combine it. It's 0, but also even if we were looking somewhere over here, don't combine a left down shear stress with an up. Don't combine a left-right shear stress with an up-down shear stress. Okay? But let's step back and look back. The overall theme here, you have 3 forces and 3 moments. You have 6 unknowns. Fx, Fy, Fz, Mx, My, Mz. You've got 6 internal unknowns. Calculate those 6 unknowns. Do you remember how to do that? We had to do that a long time ago. Calculate those 6 unknowns and then just think to yourself, okay, what type of stress does each of those unknowns create? And then combine similar stresses in similar directions. Let's think about these neutral axes, because I think these are going to be the hardest ones right here. These 2 bending moments and these 2 shear forces, they're the hardest ones. In fact, these are going to be easy. The normal force is N over A. The torsional moment, the twisting. Which one of these moments is the twisting moment? Which one of these moments gives it a twist? Those are going to be the easiest to do. But I think the hardest are going to be these bending moments creating a normal stress of My over I, and the shear forces creating a VQ over IT stress. All right, labeling the neutral axis I think is important. The neutral axis for the shear force is perpendicular to the shear, but the neutral axis for the bending moment is the same axis that the moment is bending about. All right. The shear stress VQ over IT is a maximum at the neutral axis. Did you see that? Did you get that? If we're on the neutral axis, that's the maximum VQ over IT. You are going to have some VQ over IT if you're on the neutral axis. So in this case, if we're on the neutral axis, we've got a maximum VQ over IT versus the bending stress My over I is 0 on the neutral axis, right? The bending stress My over I is 0 on the neutral axis. Why? Because that Y is the distance from the neutral axis to the point, and if there's no distance from the neutral axis to the point, then that Y value is 0. And so you see how some of these, bending and shear stresses are opposite each other. The neutral axes are opposite each other, and also the value on the neutral axis is kind of opposite each other. So anyway, those 4 statements I think are important to remember. These 4 statements, that the neutral axis for the shear stress is perpendicular to the shear force, the neutral axis for the bending is in the direction of the moment, and then the shear stress is maximum at the neutral axis, the bending stress is 0 on the neutral axis. All right, but anyway, 6 forces and moments create 6 different stresses, and calculate all 6 of those stresses, and then combine similar stresses in similar directions. Got it? All right, let's see Let's work out some problems. See how that works out.